Hello, everyone. Welcome to day two of LRVS. We're thrilled to have Dr. Michael Howard from Erbessd Instruments. And I love these sessions because we get to be visionary, right? And today he'll be talking about the future of vibration analysis. So Dr. Howard, thanks for joining us. And
happy to be here. All right, everyone. So, oh, it did it again.
Yeah,
there we go. Sorry about that. Now this is not being my friend. Sorry. Let's try that one more time. There. I'm not used to this platform, everyone, so I apologize.
No worries. We can see you now. We'll get.
Excellent. So, hi, everyone. My name's Dave Howard. I'm the CEO of Erbessd Instruments. Really want to thank everyone for the opportunity to present here at the Lubrication and Reliability Virtual Summit. It's certainly my pleasure, and I hope that everyone's able to garnish a little bit of information from what we're going to be talking about today. So, as I said, my name's Dave Howard. I've been in this industry for probably about 25 years. Started my career in the United States Air Force as a jet engine mechanic and jet engine engineer, and then moved into various roles of increasing responsibility throughout my career to where now I'm the CEO here at Erbessd Instruments. So what we're going to be talking about today is the emerging trend of IoT deployments using wireless technology. As you may or may not be familiar with accelerometer technology and the differences between accelerometer technologies, we're going to spend a little bit of time discussing the basics and then get into comparing and contrasting those differences and how they can be applied in the machine health monitoring industry. Today, it's a pretty interesting concept to me because technology is taking such big leaps and bounds in the IoT space as it specifically relates to wireless sensors. I think that and I hope that you're going to find that some of the technology that was previously available, maybe 3 years ago, has so greatly improved that it can actually be applied for machine health monitoring and be a very robust solution for machine health monitoring and very advantageous to your reliability initiatives. So today's topic is microelectronic technology, MEMS sensors. We're going to be talking about machine health monitoring and a case study between MEMS and ICP accelerometers. So we're going to talk about first just some very basics. You know, machines make the world go round. I mean, we see them every day in our daily lives, whether it's driving in our cars, dealing with our HVAC system in our home, plumbing systems, and everything we do professionally. So, you know, machines, as I said, they can be a number of different applications. They can be electronically actuated, electrically actuated, mechanically actuated, hydraulically actuated. But in general, machines transmit forces. They transmit forces, motion, and energy from one part to another in a predefined or predetermined manner. So, we're all in this business. So we're going to do some basics, but I really want to bring it all together in the end. So just bear with me. Machine health assessments are pretty much the equivalent of a physical for your machinery. So when you think about wireless technology, I always tell people who aren't familiar with what we do here at Erbessd Instruments that, we're the equivalent to an EKG for a machine. That's not to say that, we're the doctor. However, we're the tools that the doctor may very well use. So machine health assessments are pretty much like a physical for your machine. And machine health monitoring systems are critical for estimating the health of a machine and its components, especially critical machinery. Vibration analysis, one of our core technologies here at Erbessd Instruments, is one of the longest regarded indicators for condition monitoring of rotating equipment. But that's not the only one. I mean, obviously, there's lubrication analysis, ultrasound, infrared thermography. Uh, the list goes on and on. Motor current analysis. There's so many different predictive technologies out there, and those technologies continue to develop and continue to be improved over time. That understanding what's available and staying on top of what's available today versus what was available 25 years ago when I started in this industry, or 5 years ago, it's night and day. So yeah, so that's kind of just a quick basic. Any vibration in particular has two very measurable, quantifiable variables. Amplitude, how far. Amplitude is the intensity, and how fast, the frequency, an object moves helps determine its vibration characteristics. The term used to describe this movement, these terms are, frequency, amplitude, and acceleration. The vibration signature that we look at is of a machine is a characteristic pattern of vibration. It's all mathematical. So when we're looking at bearing fault frequencies, gearbox frequencies, all of these things are mathematical calculations based on the engineering and design characteristics of each machine. And based on those mathematical calculations, we can identify things like oil whirl and bad bearings, or a bad inner race, or a bad outer race, or a poor gear mesh frequency. There's lots of different things that can be identified: resonance, natural frequencies, all sorts of things. So what you see here, this is a typical time waveform, and it's using acceleration modeled with respect to time. So we have a 10-second time domain, acceleration in G's, and that's kind of what we're looking at when we're looking at a waveform. And then that waveform can be post-processed into an FFT, and that FFT tells us not only how bad the problem is based on amplitude, but also typically what that problem is. So, many of us are very familiar with these rules, you know, standard kind of rules of thumb, like a dominant peak at 1 times the turning speed of a machine is typically indicative of imbalance. A 2 times peak at turning speed is typically indicative of misalignment, and so on. So when the vibration analyst is looking at these spectrums and waveforms, they're diagnosing, much like a doctor, what they're going to find. And what's really interesting about what's happening in the IoT space right now is accelerometers are changing. So when we think about accelerometers, I mean, there's an accelerometer in my cell phone. That's what causes the cell phone to convert from landscape to portrait mode. So, you know, as simple as it may sound, that's an accelerometer. It has diagnostic capability, while limited in this particular device. Those types of accelerometers are MEMS accelerometers. So getting into accelerometers, what an accelerometer actually does, it's a tool that measures proper acceleration, where proper acceleration is the acceleration, the rate of change of velocity of a body in its own instantaneous rest frame. So in this case, what you see on the left over here is a MEMS accelerometer, where we're measuring triaxially X, Y, and Z. And you can also measure pitch. So that's where, in the case of a cell phone, translating from portrait to the landscape mode, is one of your pitch characteristics. So there's basically two different types of accelerometers out there. There's AC accelerometers and DC accelerometers. So AC accelerometers, like you see here, are AC coupled, and they can't be used to measure static acceleration, such as gravity. Most AC response accelerometers use piezoelectric crystal elements for their sensing mechanism. So let's talk about the different types of forces that can be measured using an accelerometer. Um, let's see, a static force. Static forces are forces that are constantly being applied to the object, like friction or gravity. This is where AC accelerometers don't really have the capability to measure. They can't measure static forces like gravity. Centrifugal force, like a frictional force particular to a circular path. So that's another typical measurement characteristic. And then talking about accelerometers and AC accelerometers in particular, piezoelectric materials that are used in these types of accelerometers are materials that have the ability to generate an internal electrical charge from applied mechanical stress. So the electrical charge is directly proportional or related to the mechanical stress that's being applied to the machine. And that's how the AC accelerometers work. Now, DC accelerometers, or DC coupled, can be used to measure both static as well as dynamic acceleration. So there's two different popular sensing technologies out there for vibration measurement. One is an AC, as we previously discussed, and now DC accelerometers. DC accelerometers are typically referred to as capacitive, or I'm sorry, there's capacitive and piezo resistive technology. So again, static forces are things that are constantly being applied to an object. So this is where DC accelerometers have the ability or the advantage over an AC coupled accelerometer. So let's talk about MEMS accelerometers in general. So MEMS stands for a Micro-Electro Mechanical System, and it applies to any sensor manufactured using microelectronic fabrication techniques. It's an electronic component in its entirety. So it's not like when you're using a piezoelectric crystal accelerometer where the crystal has its own means of measuring the mechanical force applied to the machine. MEMS accelerometers are also one of the simplest to apply, just because they're so small, so low cost, and up until recently, they were not as accurate or not as robust for machine health monitoring. But that's up until about 3 to 4 years ago. So, um, pros of MEMS accelerometer when or a MEMS accelerometer when it comes to condition monitoring. MEMS are great for machine health monitoring, especially now, today, in the past, say, 4 years, because you can actually achieve very high frequency response ranges and dynamic ranges. So, as an example, one of the MEMS accelerometers I'm very familiar with has a frequency response range of 0.5 hertz to 10 kilohertz. Well, that's great for most 1800, 3600, and below RPM types of assets. They're very economical as well, and they're highly integratable, meaning companies like ours, and there's others out there, can easily integrate these into wireless sensor technology, and that helps reduce the cost of deployment and ownership over time. So let's think about a triaxial accelerometer, AC coupled, kind of an old school style, like an AC 115 from CTC. Great accelerometer, great company, but at the end of the day, it's around a $600 sensor. Before you wire it, before you terminate it, before you run conduit, anything. So if you're doing an online installation where you're measuring an asset that or you want to monitor an asset continuously, the wired AC coupled accelerometers are very cost prohibitive because they're expensive. You then have to wire them. You then have to run conduit typically, and it can become a very laborious process. And beyond being laborious, it's just more expensive. MEMS have brought a small size, small weight, and lower cost solution to the market with very comparable and very reliable characteristics, like the frequency response range of 0.5 hertz to 10 kilohertz and the dynamic range up to 32G. So believe me when I tell you, if you have a machine shaking at 32G of acceleration, you're going to see it. So when somebody says, "Well, these AC coupled sensors are better because they can measure 100 Gs or 500 Gs," sure, in certain applications that's going to be the right solution. However, in most applications, 32 Gs is gracious plenty. So let's take it a little bit of a step further. This isn't to say that wireless should replace wired, or that wired is better than wireless, or wireless is better than wired. What we're saying is that they're using the right tool for the job. Critical assets, gas turbines, turbo machinery, things like that. We're not going to be replacing hardwired sensors with wireless sensors in that case. Another very unique pro to MEMS accelerometers for condition monitoring is they have a very adaptive topology for easy analog to digital conversion and DAC interfacing, digital to analog interfacing. They scale up very quickly from a manufacturing perspective. We've got a dozen or so pick and place machines that are populating boards with our MEMS accelerometers on all of our sensors almost every day, and those things are happening very fast, very automated, very repeatably, and with high quality. They're also very low power, and while there's low power piezoelectric crystal sensors out there, they're still wired. And that's not to say that they're bad or good. It's just that understanding the difference. So MEMS accelerometers have a very low power. Typically 3 volts is nominal, and you can run a MEMS accelerometer for years off of a single 3-volt coin battery, as an example, like a CR2477. They're also very robust in very challenging environments with high shock tolerance. Like I said, we can get up to 32 Gs, but they're also, because they're an electronic component, they can be, and they're in a very small form factor, they can be easily sealed and put into a housing, kind of like this one, that allows them to be quickly, easily deployed at a low cost, and provide similar, if not the same or better results in terms of machine health monitoring. So I put the caveat on here: typical drawbacks of MEMS accelerometers 3 years ago. Um, 3 years ago, the industry was very different. There's a lot of very smart people in the MEMS accelerometer space. Ed Spence is a great resource for anybody that wants to learn more about MEMS accelerometers. I'm happy to discuss it as well. But typically, 3 years ago, and even today, MEMS accelerometers suffer from a high floor noise. They have a poor signal to noise ratio with a limited dynamic range of up to 32G or less than 200G. Now, that's 3 years ago. Let's fast forward to today. Um, there's all of these drawbacks have been addressed via improved manufacturing processes. Like Analog Devices has a sensor called the ADXL1002. That sensor actually is a single axis MEMS accelerometer with floor noise of around 60 microGs per square meter, which is equivalent to, if not better than, most accelerometers out there, that most piezoelectric crystal accelerometers, and it comes at a lower cost. So that's kind of putting it into perspective. These drawbacks that you see here from 3 years ago have, as I said, been addressed by improved manufacturing processes, improved R&D, or improved integration and processing on the part of the systems integrator. Like us at Erbessd Instruments, we've applied various filters and various things to eliminate these drawbacks, to mitigate these drawbacks, or in the case of the ADXL 1002, Analog Devices has eliminated the floor noise issue that was present in previous generations of that sensor. So, typical MEMS accelerometer. This is, my one of our sensors. This is the Phantom Expert. It's 8, 16, or 32G silicone micro machined accelerometer with an integrated 2048 byte buffer for storing data on board. They have the ability to be oriented based on the different axes. They can be mounted using a an adjustable mounting pad that can be adhesively applied to the machine. They can be stud mounted just like a traditional accelerometer, and they can also be magnetically mounted as long as you're using the appropriate shielded magnet. They also have a great, because they're such a low power when we talk about MEMS, because they're so low power, they can be programmed in many different ways. One of the ways that we do this in MEMS technology that's very hard to do in piezo sensor world is we have these sensors configured so that they can monitor velocity RMS, as an example, every 30 seconds, calculate velocity RMS, and then wake up if there's a trigger. So they have, if I say wake up on high vibration. So you can apply a value and say, hey, look, if velocity RMS is found to be above this level, then perhaps you should wake up and take a full recording for waveform and FFT analysis by a vibration analyst. Um, that's really important because those types of functionalities in the ICP or the piezo sensor world are can be also applied. However, there's hardware integration that needs to be done. Typically, an online system like previously in my life, I was the director of engineering and customer success at Comtest Instruments, and our VB Online was a hardwired 24-volt device that powered piezo sensors and could wake up on high vibration and do many things like that, but it required an additional device. That device was the VB Online, which was the size of a loaf of bread, and came at an additional cost. Whereas all of this functionality within MEMS technology can be integrated within the actual circuit of the technology or within the product. Phantom or MEMS in general has very high shock survivability, where an ICP accelerometer, if you drop that accelerometer from a very high, you're on top of a ladder, it drops, hits the ground, guess what? You're going to have to send it out for calibration. Um, Phantom and digital MEMS accelerometers have very high shock survivability. They have excellent temperature performance. And like I said, they're user configurable. It's like a microcomputer built into the size of a sensor versus having a ICP sensor like this one going to a hardwired device that does all of the processing and everything. And that comes at additional costs, that comes at additional labor, additional cabling, all the things we've already discussed. The MEMS technology also has the ability to apply different filters, like a digital high pass filter. They have a very small footprint. Their signal bandwidth is excellent, up to 10 kilohertz, and the sample rate is excellent as well, up to 25,600 hertz. So at this point, we're kind of seeing that by reducing the noise floor, by implementing engineering controls, you can get the same performance characteristics, if not better, out of a MEMS accelerometer versus an ICP accelerometer. Again, that's not to say that an ICP accelerometer should be replaced or a MEMS is better than, one is better than the other. It's just to say that their equivalency has finally been achieved in the market, in the world of vibration sensor technology. As long as you understand the the equivalency in terms of technical characteristics, and then also understanding that a MEMS sensor that's battery powered is probably not best suited for a critical asset that if the plant shuts down or that asset fails, there's a threat to life, environment, or significant threat to process. So that's where, okay, in highly critical applications, hardwired solutions are always going to be the best, at least based on technology that's available today. Perhaps in 3 years that might change and we might be having a very different presentation. But as of today, highly critical assets that have a high threat to environment or high threat to life and safety, those types of things, it's best to continue with that hardwired environment where balance of plant applications and, where you have maybe not as critical an asset, MEMS technology is excellent for those. So what we see here, this is a typical ICP accelerometer. It's a sensor that generates an electrical output proportional to the applied acceleration. The electronics within it are seen on the slide, and what they do is they convert a high impedance charge signal generated by a piezoelectric sensing element into a usable low impedance voltage signal that can be readily transmitted over traditional two-wire or coax cable to any data acquisition system or even a readout device. There's lots of different piezo sensors, but essentially this is a good example of it. You have the microelectronics, you have your stainless steel or metal housing, your piezo crystal, mounting base, lead wire, seismic mass, and your electrical connector to apply that electronic or the electrical charge. So benefits of ICP accelerometers. We've talked about MEMS and and their benefits, but again, that's not to say that they're better than ICP. It's just that there's different technologies available, and understanding the technologies is very important. So benefits of ICP: they use a standard coax cable or ribbon wire for connection. They connect directly to so many portable instruments and so many online measurement devices and readout instruments that they're very widely deployed and very widely accepted across the industry and across vendors. Um, they can drive long cables without noise, an increase in noise or a loss of resolution. 100 meters of cable isn't unreasonable, but that's also in MEMS world, depending on the wireless protocol you're using and things like that. You can get equally as much wireless range as you can cabled range. So and then ICP accelerometers are impervious to floor noise as opposed to MEMS accelerometers, and they also have unlimited sample rates. So if you need very high sample rates, you're doing a very robust engineering study, you're probably going to be using an ICP accelerometer in that regard. However, um, as I said, the engineering controls and things that have gone into place in the MEMS world over the past 3 years have eliminated that floor noise issue that was present previously. So, yeah. So drawbacks of ICP accelerometers for condition monitoring, they do have a limited temperature range. So do MEMS accelerometers. The electrical characteristics, the sensitivity, the range, and discharge time constant are fixed within the sensor. Um, they also have an expensive installation that we've already discussed and a very high cost of ownership in comparison. They have a low frequency roll off. It's roll off is the steepness of a transfer function with frequency, particularly in the electrical network analysis sensitivity. It's defined as the input parameter change required to produce a standardized output charge. So they also require a higher power than most MEMS, well, all MEMS accelerometers that are commercially available. Most ICP accelerometers, piezo sensors are 24 volt, and MEMS sensors are 3 volt nominal typically. This is a typical ICP accelerometer, another great product from CTC, an AC140. It typically contains a welded stainless steel construction for survival in harsh factory environments. MEMS accelerometers, depending on the systems integrator or the manufacturer, they can have stainless steel construction. They can have ABS plastic. They can have the same survivability, just maybe perhaps different materials. ICP accelerometers usually have a dual case design, shielding the sensor element from the RFI and EMI interference. So radio frequency interference and EMI electromagnetic interference are real things out there. In some MEMS sensors, a high electromagnetic interference field is actually not a good thing, because as in the case of the phantom sensors from us, we actually use a reed switch to activate the sensor, and that reed switch is activated magnetically. So, this isn't the best application for a MEMS sensor from Erbessd, as an example, because a high electromagnetic field might cause the reed switch to continuously reset and then kill the battery. So again, understanding pros, cons, benefits of both helps us determine what the right tool for the job is.
Hey, David,
Another element, yes.
hey, we've got 1 minute to go, and there is a question. Just, do you have any final thoughts, and are you able to
Yeah,
take?
I'm sorry. Well, I'll just throw this up there. Here's, MEMS versus ICP. This is a great slide that, you can do a compare and contrast. I didn't realize it was such a short presentation. Sorry about that. MEMS accelerometers for condition monitoring, like I said, key advantage, small size, low power, easily deployable, and low cost. So here's a bunch of references. I'm happy to share the whole slide deck with the folks at the summit, and you guys can post that, publish it, do what you need to, so that folks can do more with it. So
Perfect. All right.
that's it.
Awesome. Thank you. So what we'll do is, if you've got additional questions, please put them in the chat, and David will get back. Connect with him in the app, and I think in his speaker profile he's got maybe a LinkedIn. I don't know, but certainly through the LRVS app you can connect with him, and just do one-on-one questions there. But David, thank you so much for sharing your knowledge, right?
Yeah, no worries. Just quick answer for Matt Moore. Matt had asked why MEMS accelerometers typically do not have a calibration certificate. That's because they're solid state devices. They're either in spec or out of spec. If they're in spec, then they obviously are shipped and they meet the specifications of the data sheet, but they can be issued with an accelerometer calibration certificate just as much as an ICP accelerometer can. In fact, we can do that, and many vendors do.
Perfect. All right. Thanks for that. Thanks for joining us, and enjoy the sessions.
Great. Thanks so much. Have a good day.